Before I start my presentation, I'd like to acknowledge some people from Fortes that helped me, Werner Kramer, Alje Vrieling, and some people from Dotaris like Judith Sumiar and Martin Verlaan, Stef Rummel. And also Olda Rakovec, who's now working with Luis Samaniego in Leipzig. Yes, what provides forecast skill, hydrologic forecast skill? I think this was mentioned in several talks. Boundary conditions, maybe coming from very good NWP. Initial conditions, and then you can of course improve your initial conditions through data simulation. And then last but not least, the quality of your hydrological model, hydraulic model or model chain, depending on your setup for your area. And of course, you can do some statistical processing to further improve the results. This is basically the same plot. We have NWP, we have a forecast chain. Sometimes this is lumped all together in one model. Sometimes it's like a chain of models, which makes it very complicated to do the data simulation, post-processing, etc. for all these different models separately. And then if you're in a coastal area, maybe you also have a storm surge model. So as I said, this can be complicated depending on the forecasting system that is being used. We see a lot of different forecasting systems, and data simulation is quite a challenge when you have very many separate models run together. What is data simulation? We start with a generic model formulation, the model M, which time-dependent state variables, state time-dependent forcing, parameters. I personally prefer parameters that are not time-dependent, and there's of course noise that's also time-dependent. And we try to improve the model outcome by applying systematic perturbations to the model. And we try to optimize using the knowledge of model uncertainty, using multiple instances, using a certain data simulation method, and we try to use the observations as a reference to do the evaluations. I started working in data simulation from 2004 onwards. One of the first applications was on lumped hydrological models. Soon thereafter, I started working on a hydraulic model for the River Rhine, and also got interested in developing generic tools for data simulation, because in principle for every application the methods that are being used are the same, only the model is different. So it makes sense to develop generic tools and then be able to switch easily the model between applications. That's why we started working on something like called the DA tools. And this was developed for the Rhine River hydraulic model. We simulated water level along the River Rhine, 14 locations. And this went operational in 2008 and has been running since without too many problems. I don't think any problem. So this is still running at the Rijkswaterstaat in the Netherlands. But of course, after 2008, we started merging our initiative, DA tools, with another group from TU Delft, Delft University of Technology, and a small firm, Fortech BV in the Netherlands. And then we came up with something new, which we call OpenDA. First part of my talk will be on OpenDA. What is it? How can you use it? Second part of the talk will be about some applications. OpenDA is a generic toolbox for data simulation and parameter calibration, uncertainty analysis in a generic context. It contains a library of methods. This library is growing. And basically what OpenDA is a set of interfaces that define the interaction between the components. And the component that is in control is the method, the algorithm. And the algorithm can then start the model, stop the model, ask for an observation, ask for the states, and in that manner can control the whole process of running the data simulation. It's open source. It has an LGPL license. It's written in Java, C, and Fortran. And it's available for Windows, Linux, and Macintosh. So it's basically platform independent. There's a website, and there's an association This association is open, so people can join. And recently, besides the three founding fathers, DHI started to join this activity as well, which is very good. And with these people, we maintain the code and make sure there are releases once in a while, and that the manuals are there, and there's a course you can do. These types of activities are being organized. Why is this so important? Because personally, I think it's more efficient than development for individual applications. Of course, you can tailor maybe for individual applications slightly better, but you lose a lot of benefits, like shared knowledge between applications and people. You cannot talk about it with other people. It's only in your own model setting. You can also more easily develop other algorithms together with universities and bring that in and test it. You also benefit from other people that contribute new methods. Optimize the building blocks for computational things, also problems you encounter, and things that come up. And there's a development template for connecting your model, connecting another algorithm. And I think also if you start comparing different algorithms, it's very useful to do that in one framework instead of that all these methods are developed for individual applications and then do a comparison, because then you're not really sure what you are comparing. There's a GUI which is you can run it completely standalone, both for the data simulation and parameter optimization or uncertainty analysis. This is included in the release. I will also talk about how to use it within the Delft-FEWS framework, which is mainly the focus, how I use it in daily life. The architecture is like this. You have several configuration files, XML files that you have to fill out, and then the algorithm has an interface, and all the observations have an interface, and the different models have a different interface. And this makes it possible to communicate between these different components. You can couple your model in two different ways. Black box, if you don't have the code available, you use a black box coupling approach. You just use the model input and output file and state files, and you have to write some tools to read and write these files, and stop your model, etc. And you also can develop a native model wrapper. So the model will act as a library. This is, of course, important. This computational time is a problem. Of course, this takes more time to develop. So normally people start with a black box coupling and maybe reconsider later to switch to a native model wrapper. As I said, I'm mainly using it within the Delft-FEWS platform. I don't want to go into depth about all the things that are in Delft-FEWS, but I like to focus on how models are being run within the Delft-FEWS system. This box being the Delft-FEWS database, you are able to run models through a general adapter, and the normal way of doing that is you export some data, you convert that data for the simulation model so it can be understood by the simulation model. Then you execute this simulation model. You get some data out, you transform that to a specific format, NetCDF or XML type format, and then it's inserted into the database again. If you now move to OpenDA, if we include the data simulation, this slightly changed. Basically, OpenDA takes over the role of the pre and post adapter, and the data comes from the system, and the method is then in control. And if you want to get rid of the conversion, you can do everything in memory with your simulation model and run it like this. And this is basically then a standalone application that is being executed and controlled from the Delft-FEWS platform. I'll show two examples. Slightly longer on the Weerts case in Belgium. And at the end, I will tell something about ongoing work for Tennessee Valley. First, start with the open source, Upstream distributed hydrological model for Belgium. This is state updating with a distributed hydrological model. This was already published in 2012 by Albrecht et al. We studied the effect of updating frequency, number, and location of streamflow gauges in a distributed hydrological model. We used the HBV96 model. We used the calibration, which is uniform over the whole basin, used by the Dutch government. So basically it's a copy of the Dutch model for the Ourthe basin, except that we replace the max bus procedure with a kinematic wave to route the water over the grid. This is the Ourthe catchment. It's in Belgium. There are multiple gauges. The triangles are the observation points. 1 is the outlet. 3 is somewhere in the middle. 5 is somewhere here, and 6 is somewhere there. So these are tributaries that come together here and then flow here out of the Ourthe catchment at Tabreu. We use a 1 kilometer square grid, and as I said, the calibration is basically taken from the operational model. So we conducted several experiments, updating at different frequencies, every 6 hour, every 12 hour, every 24 hour, and also using different amounts of discharge gauges in the catchments. So option A here is basically only simulating the outlet. Option B is basically simulating only the upstream gauges 5 and 6. And option D is simulating 1, 3, 5, and 6 at the same time. And as you can see, going from updating every 24 hours to 12 hours, you see a large jump. But from 12 hours to 6 hours, the difference is less. And based on this, results in terms of RMSE were achieved using all observations. And given the travel time in the system, it takes about 24 hours over the whole of the catchment. We thought that, and also given the results in this plot, that 12 hours seems to be the most appropriate choice to do the updating. Also from an operational perspective, because every time you have to stop the model and do the analysis, this will cost a lot of time. So ideally, you don't want to do this. You want to do this as little as possible. And what was also shown that the most sensitivity is in the routing store. So we do the update, but the update doesn't really progress to the hydrological states, soil moisture, upper zone, lower zone. Then Albrecht went on, and we focused on operational aspects of asynchronous filtering, which is a method that was developed by Sakov et al. In 2010. This method is available in OpenDA. And we tested this asynchronous method, and this method basically makes it possible to assimilate multiple observations at the same time. This is not very difficult. You just, I go to the next slide. You have the normal common filter equation, but you basically augment the state factor with past forecasted observations. So the model equivalent of the observations, and use those, and in that way you can use the past observation as well. Then I will try to explain how this works and what the benefit could be. Or here are the gauges that I already mentioned. 1 is the outlet, 3 is somewhere in the middle, and 5 and 6 are the 2 tributaries. If you look here, the gray band is basically an ensemble open loop run. These are the observations. So for gauge 1, you see that the model is somewhat too dry and should basically move up a little bit to describe the measurements, except for at the end of the run, it's in the middle. Gauge 3, you see that the ensemble is somewhat too high, and for gauge 5 and 6, you also see that the ensemble is relatively high and should maybe brought down. Then I come to this complicated figure, which shows basically the mean innovation for all of the states for different case studies. This is asynchronous with W is 0, basically means this is same as ensemble common filter, except we use a window of 0 length or 1 length, and we only use if I go here with the pointer, you only use the outlet as an observation. So if you remember from the previous plot, at the end of the run, when we do the analysis, the observation was in the middle of the ensemble. So basically, nothing happens to the discharge, water level, and soil moisture, and upper zone. If you then move on and use the asynchronous Kalman filter with the past 11 observations, this changes basically. Remember that we were too low with the ensemble, so water has to be added, and that's what you see basically. The red colors indicate that water was added. The mean of the innovation is negative. With this definition, that means that water was added. And you see that it propagates also to the soil moisture and the upper zone store, but mainly to the routing part. Now going again to the Kalman filter case, ensemble Kalman filter case, where we only use the last observation, but now also include the last four, all the gauges, 1, 3, 5, and 6. You see that the picture changes. Remember, this was too high, but the other ones were, this was one too low and the other ones were too high. So it's more complicated, but you see some, you get some distribution of the update by the filter over the grid. And then if we move on to the asynchronous one, using all the gauges, using all the past 11 observations of all the gauges, you see that the innovations are further distributed over the catchment domain, and seeing that most of the innovations, basically, for instance, for the upper zone and the soil moisture, are being done here for gauge number 6. And if we go back to this plot, you also see that gauge number 6 is, the ensemble is too high, so water has to be removed. And in this way, the asynchronous filter is able to make this update more distributed. So we try to test this for the 8 largest flood peaks. We only perturbed the soil moisture reservoir with a temporal spatial correlation using 36 ensemble members. The sensitivity was tested over the simulation time window. We used 3 time windows, 0 hours, 5 hours, and 11 hours. So this is 1 measurement, this is 6, and this is 12. And we also tested partition state updating schemes. So we had no update. We update all states. We left out soil moisture, and we only are updating H and Q, so only the routing part. So the experimental setup is similar as the previous setup. We use the same model. This is all done in OpenDA. The rest is the same. So I can skip this slide and go on. And here are the results for Tabreu, the endpoint of the run. Here you see the crosses indicate no update, so this is no data simulation. The red, the solid lines, and the green solid lines, and the blue solid lines indicate ensemble Kalman filter runs. The dashed lines indicate the assimilation window of 6 hours, and the dashed line of the dotted line with the points indicate 11 measurements. And what you see is basically surprising that the run with HQ here is apparently the best, but degrades pretty quickly. If we don't take into account the soil moisture, we see that we get good results, and they stay okay for quite some time. And also you see that the assimilation window of 11 hours seems to be slightly better than a simulation window of 5 or 6 hours, or 12 hours to 6 hours. Of course, you can argue you assimilate different amounts of measurements. Of course, that's true. But from the previous study, we knew that the difference between updating every 12 hours or updating every 6 hours was small. So it seems, and this also gives gains in computational time. So it's probably most effective to use something like 12 hours for this basin. This is the validation point. This was not used in the assimilation. we see more or less the same results for this point. And this gives confidence that yeah, this works quite well. The second example is work in progress. This is done together with RTI, Anchor, and Delft-FEWS USA for Tennessee Valley Authority. And the main goal here is to investigate if we can guide the manual modification process that was mentioned yesterday, to guide this process and realize considerable time gains, because of course this is a time-consuming process if you have to adjust phase for each basin. Yeah, this is quite time-consuming. So we are investigating automated data simulation methods to guide this process. The challenge here is also the setup of the system developed for the National Weather Service. Basically, all the models are different components. So the soil moisture model, SAC SMA, is a different model. So these are different components glued together in a workflow, which makes it difficult. So it's not one big model where you can update all the states at once, but you have to think about all these different models after each other and how to do this. So that's why we wrapped Delft-FEWS via our web service in OpenDA to enable the parallel execution of the workflows and the chain models within these workflows, and then run this in a data simulation framework. And the goal of the exercise is to test different algorithms to see if there's a specific method that is more appropriate to use or has better properties than others. And at the moment we are testing the ensemble Kalman filter, the asynchronous ensemble Kalman filter, and the particle filter. This is a work that's ongoing, and we are hoping to show the verification results, full verification results at ATU. And the current idea that we have is that the ensemble data simulation analysis provide a single mean estimate of the state at the T0 at the start of the forecast, and then you can basically calculate the difference with the state used in the deterministic model, and in that sense provide a modification suggestion to the forecast. And then the forecast can choose to accept that or make its own changes to the model. Here are some results which were prepared together with Jan Verkade, who also spoke this morning. At this side, this is for the upstream catchments. This is for Powell, which is linked to this segment name. At this side is the asynchronous ensemble Kalman filter, so that's to your right, and to the left is the ensemble Kalman filter. And starting here from the largest lead time, so this is 5 days ahead, 4 days ahead, 24 hours ahead, and 12 hours ahead. You see that using perfect rainfall as input, as you can see, some of the peaks here are not captured, not by the asynchronous ensemble Kalman filter or by the ensemble Kalman filter. Here it seems that the asynchronous Kalman filter is performing better 7 days ahead than the ensemble Kalman filter method. And then if we move up to the start of the forecast, to the real, how do you call it, T0, you see that the results improve. Here, for instance, ensemble Kalman filter 12 hours ahead is possible to describe the observation completely. But yeah, but it wasn't able to do this 7 days with a 7 days lead time. Then if we move to a downstream location, so downstream of Powell, there's Arthur. Here we use the observation, also the inflow of the observation, and not the model results of Powell. You see that the differences are not so great, and the models seem to behave pretty similar, or different data simulations seem to behave pretty similar. And this looks quite encouraging. But of course, there are also some problems that you can see. For instance, here, this is again the upstream model. What you can notice here is that there's a very strange large peak here, forecasted 7 days ahead, and that stays in It stays in the simulation up to 12 hours. Let's get rid of this picture actually, but and that has to do with apparently that this is the precipitation, and apparently this precipitation doesn't fall. Of course, this is provided to the model and gives a large peak here, and that's what you see. So you cannot get rid of it. If this picture wasn't here, you could see that the ensemble Kalman filter apparently was able to remove this peak or noise from the simulation. So going to the downstream location again. Again, 7 days ahead it looks very good. 5 days ahead it also looks very good. 4 days again, and then after, if you come closer, you see basically that the results are less good. Apparently there is some update being carried out, and then this results in problematic behavior by the model. So there's an overshoot basically here, and it's for both methods that's basically the same. That's apparently there's some updating being done, and then we either trust the measurement too much, and then we add too much water, and then in the forecast you are in trouble because you get an overshoot. So the picture is a bit mixed. It looks very good and nice and seems to work pretty nicely, but sometimes you get strange results because of these overshoots. And this could be either linked to that we trust the observation too much, or that the input data is just not good enough to do these types of simulation. So you should basically look at better precipitation data, and then you can do these types of simulation studies. We also did a CRPS comparison using sample climatology as reference forecast as a function of lead time. And this is the upstream location, this is the downstream location. Overall, the differences are not very great. I would tend to say that the asynchronous ensemble Kalman filter, with its updating every 12 hours, seems to be working quite well here, compared to the ensemble Kalman filter, gives slightly better results. So concluding remarks, a lot of research has been conducted the last couple of years on the topic of hydrological ensemble data simulation. And I think in operational hydrological data simulation, there's not yet a preferred data simulation method. As shown, the asynchronous one seems to be promising as an alternative to ensemble Kalman filter. Maybe the variational methods shown by Rodolfo seems to be very promising. And during the presentations in Austin a couple of months ago, there was the maximum likelihood ensemble filter presented, which is basically a hybrid method. You don't need a joint, but it's also like a variational type method, and that also showed promise. I think operational ensemble data simulation is becoming feasible, and obstacles to start using it and testing it, because I think that's the first step you have to do, start testing it in an operational setting, are mainly institutional. At least that's what I see. I mean, either the resources aren't there, the forecast process is not yet completely clear to the forecasting agency, or there are other priorities. And finally, I think community-based generic modeling data simulation tools are needed, and useful tools also to cross the bridge between the research and the operations. If we work with these generic data simulation tools, it's much easier to transfer from research to operations, because you use the same in both worlds. Thank you.
Very much, Albrecht. Question? Yeah. Thank you for the presentation. Very interesting to see how the number of observations distribution of the output to the level. I have a question about the results. Go back to the simulation updating before. So we could see that the updating of the routing however, H-SAF is not that consistent.
Correct. You mean between B and C?
Yeah. Maybe because hydrologic is one more.
One more? This one.
Okay, right. So the updating of the H-SAF sources is not that consistent, but carried out nevertheless. The most updates are being done to those sources. So have you tried to remove them from the updating scheme? Does it make sense? Or only the update acetone maybe?
No, we didn't do that. We only removed the soil moisture. Maybe it was tested in the beginning, but yeah, basically it doesn't make sense to remove the routing part, because from previous study we know that most of the updates take place in the routing part, and the routing part also provides, at least the first 24 hours is very important for the hydrological forecast. So in my opinion it doesn't make sense to remove the routing part, because that contributes a lot to improvement in skill.
Okay. Yeah, probably the most sensitive.
Yeah.
And maybe another question that show the augmentation of the space vector, just for clarification. So you include paths to simulate the discharges into the space vector, right?
Yes, the observations, yes. The model equivalent of the observations in the past.
I see. Yeah.
Yeah.
Thank you.
Yes, I wonder if you have ever evaluated also the impact of this assimilation to neighboring and onboard basins, because I've seen very little of this kind of evaluation.
You mean the basin next to here? Actually, I had a master student working at this this year actually. We followed the same approach for whole of the Mews basin and do the update for the whole Mews basin, which consists of like 14, 15 of these types of lump catchments. And there you see that you need to, yeah, you can do the whole thing. I mean, it's working mechanically, but at a certain moment when the streams come together and you try to do the update, but the behavior of these basins is quite different. So then, yeah, you're basically in trouble because one basin is affecting the other and you don't want to do that. So you need some kind of localization method, which is typically applied also in these types of data simulation schemes. And we are working on that, but it's not yet ready to be used. But then basically you do only the update for the area for which the measurement is valid, so to speak. So you need these types of localization methods, otherwise you can get very strange results. So yeah.
You mentioned also the use of OpenDA for tracing process, and what's your experience using OpenDA for the
I've not so much been involved in the calibration part, but yeah, basically it's open. You can use it. From my point of view, calibration, it's so easy to set up a calibration also within, at least for researchers. I mean, for organizations like forecasting organizations, I think it's different. But for research, it's so easy to set up a calibration scheme in Python or whatever. So it's for those types of applications, I don't think the calibration toolbox will be used quite a lot. But for packages, software packages, or forecasting agency that want to do calibration in a standardized way, I think it's very useful. These types of software.
So they run in parallel? But they run in parallel? You're doing like both processes at the same time? Or like?
What, the calibration you mean?
Yes, like there's a group of the calibration and the.
No, this is separate. So you don't. The calibration is an offline study. Yeah.
Okay. Thank you very much.
Okay. Thank you.